Thank you for choosing Synovision Medical Imaging Products. Today I will introduce the function and operation of the post-processing software application, Tumor Perfusion Analysis (TPA). The mathematical model used in TPA is the deconvolution method. Therefore, the required injection flow rate is not too fast. About 4 milliliters s is fine. The TPA application is only suitable for the analysis of the single blood supply organs in the head and body. Precautions for tumor CT perfusion scan. 1. Due to the requirement of the algorithm model, the contrast agent requires a flow rate of 4 to 5 ml/s, and an 18G or larger trocar needle has to be used. 2. The amount of contrast injection volume is 50 milliliters followed by 50 milliliters saline. 3. The patient should remain still during the perfusion scan. So, the head or abdominal straps should be used to limit the movements. 4. Perform a non-contrast CT scan before, to select the best perfusion scan level, including the region of interest of the lesion and the blood supply artery. 5. The perfusion scan series parameters setting principles should include: A. Use the widest collimation width. B. The thickness of the reconstruction should be 5 to 10 Too thin or too thick will affect the accuracy of the result. C. The scan cycle time represents the time resolution. The faster the better, but the radiation dose should also be considered. Should be within 0.5 seconds, 2 seconds. Not more than 3 seconds. D. The delay time should not be too late. 5 to 8 seconds is recommended. E. The dynamic perfusion time should not be about 60 seconds. 6. Perfusion scan should pay special attention to the radiation dose of the patient. 100 kV, 120 to 150 MAS is recommended. The scan interface. The scanning process is to scan the SCOUT image first. Perform a non-contrast helical scan. Find the appropriate layer on the axial images. The region of interest and the aortic section must be included. The layer preferably includes the blood supply artery of the tumor, and then perform enhanced scan on this layer repeatedly. That is the so-called perfusion scan. Pay attention to the SCOUT scan. The non-contrast scan and the perfusion scan all need to turn off the automatic voice. After the scan is completed, the images should be sent to the post-processing workstation for tumor perfusion analysis. Now let's focus on the analysis process of the TPA plugin. After selecting the perfusion series, load it into the TPA application interface. Note that the TPA application only supports perfusion analysis of single blood supply organs and tissues. A pop-up window prompts that the analysis result cannot be used as the only basis for diagnosis. Click OK to close the pop-up window. Now the left side of the interface is the image viewport, and the right side is the toolbar. The perfusion analysis process is generally divided into 3 steps. The first step, data correction. The second step, blood vessel definition. The third step, measurement and analysis. Now we are in the first step, data correction, which is mainly to remove images that do not meet the requirements, such as images with excessive artifacts or obviously deviated. The left side of the viewport is the axial image, and the right side is all the images of the current level in all time periods displayed overlappingly and in the form of MIP. First of all, we need to adjust the WWL to observe the image more clearly. In the left viewport, the sliding bar can be used for dynamic observation of the same level at different times. There are 2 sets of blue numbers below. The number on the right represents the current layer sorted by time. 14 means the 14th acquired image. It can also be automatically played by pressing playing. Slide the bar at the bottom or click the triangles at both ends. To switch layers. The blue number on the left side shows that the perfusion covers a total of 4 layers. The number in front of the slash is the current layer. At the top of the toolbar are some common tools for perfusion analysis, including Register, which can correct and align slightly misaligned images. Smooth image, smoothing the image to reduce image noise. Parameter, smooth settings. To set the method and times of image smoothing. Below is the series editing. If you want to delete an image with a lot of interference, click Add the image to be deleted to mark it, and then click Generate New Series. Now in the new series, the selected images have been deleted. Through the above mentioned operations, aligning and deleting and so on, we have completed the first step of data correction. Press the next step arrow to enter the vessel definition interface. In this interface, the curve at the lower left corner is the time density curve TDC. In the upper and right viewports, we can add the artery. Because the artery is small in this case, we can zoom in. We should try to choose the vertical section of the artery to reduce the partial volume effect. Then use the single Define Artery button to define the artery. After adding, we can see the time density curve is generated. Try to ensure that the curve is smooth. SP and EP respectively represent the start and end phase. Place the mouse over the arrow. We can move them. SP has to be placed on the last image before arterial enhancement. EP should be placed on the flat area of the curve after the arterial peak. Press the arrow to enter the measurement and analysis interface. Now the color maps of perfusion parameters are displayed at the bottom. Double-click the color maps to enlarge them to full screen. They are blood volume BV, blood flow BF, mean transit time MTT, time to peak TTP, and permeability surface Ps. Hold down the middle mouse key and slide to adjust the color effect. Double-click the color scale to change to other pseudo-color settings. It can also be displayed singly. Double-click again to return to the original layout. Both the grayscale image window and the time density curve window can be double-clicked to switch to full screen. Fusion display. The grayscale image can be fused with the parametric maps to locate the lesions more easily. By default, the grayscale image will be fused with the blood volume perfusion map. Right-click the blue character BV. We can choose to switch to other perfusion parameter maps. We can also switch between levels. On the left side of each parametric map, there is a color scale. The lower color indicates a lower value, and the upper color indicates a higher value. For example, in the BV parametric map, green indicates a higher value of blood volume than blue. It can be seen that the BV and Ps of the tumor is higher than that of the normal tissue, and the MTT and TTP are longer. Because the head is a symmetrical structure, we can place a midline here, and generate a mirror ROI for comparison with this midline as a reference. We can place a circular ROI in the tumor area on the right, and then click Mirror ROI to generate a comparing ROI. Pay attention that the ROI should avoid blood vessels as much as possible. The measured values are displayed in the ROI statistics table. It can quantitatively reflect changes. Finally, if we want to save the parameter color maps, the TDC curve, and the quantitative measurement table respectively, and the system will automatically save them under a series. The introduction is stopped here. I hope it will help you understand the use of tumor CT perfusion imaging and post-processing analysis software TPA.